Hi folks, we're going to take a look at page 278, number 18, and what this describes is a ride that goes around in circles, okay, and it lies on a horizontal plane, okay. So you can read the question just to confirm that this is what the ride looks like. So going around in circles, okay, and if I want to come up with an equation model, the best thing to do is to lay a Cartesian plane over this circle. So I would say that the most convenient place to put my Cartesian plane is is to have the center at the origin. Okay. Now they tell me that this ride has a radius of 4 meters. So 4, 4, negative 4, negative 4. Okay. So I've got a circle of radius 4 with center 0, 0. And they also tell me that the period is equal to 2 seconds. Okay. Now let's take a look at how the different components are moving, okay? Because what they want us to do is they want us to find a model for the x component of the point as it moves around the circle and the y component of the point, okay? So let's see how this is going to look. So as an example, let's say I start here, okay, at the top. Well, my x component is at 0. So as I move around the circle, okay, my x component goes to its maximum. And then as I move below, we see that the x component goes back to 0. And then eventually it goes towards its minimum value of negative 4. And then as I get to the top, it goes back to 0. So remember, I'm just looking at the x component. And then, of course, this starts over again. Okay? So my periodic behavior for my x component is that it's going back and forth along the x-axis between negative 4 and 4. Okay, you can make a similar argument now for the y values. So at this point here, okay, the y value is at its maximum. Okay, and as I move along, the y value gets smaller, smaller, smaller till the y value reaches 0 and then goes to its minimum and so on and so forth. Okay, so the y values are going back and forth along the y-axis between negative 4 and 4. So those are periodic behaviors. But in both instances, we see that the maximum value is going to be 4 and the minimum value is going to be equal to negative 4. So just with this information, I can already determine some of the parameters that I'm going to have in my equation. Okay, so since the period is 2, I know that the k value is just going to be 2 pi over 2. In other words, period of pi. Okay, with my maximum and minimum, I can calculate the amplitude. Now here, we should know what the amplitude is going to be because the distance between the middle and the maximum or the minimum is just going to be 4. Of course, what you could also do is just, add these together, divide by 2. Okay. Subtract them since we're looking for the amplitude. It's half the distance between the max and min. So 4 minus negative 4 divided by 2, which is 8 over 2, 4 as we expected. And we would think that the c value should be equal to 0 because the middle value occurs at 0 for the x component and also for the y component. And if you want to confirm that with your equation, well, you have that the c value is the sum of the max and min divided by 2, which we confirm is 0. Okay? Now, question is, do we need a phase shift? So if you notice in part A, they're actually telling you to use a sine function to model the behavior of the x position. Okay, now they haven't told us in what direction this is turning. Okay, so it could go counterclockwise or clockwise. Okay, they're not giving us a starting point. So let's try to use, the starting point that will hopefully not need a phase shift. Okay, so the x components have to be modeled by a sine function and the y components by a cosine function. So I know that sine is going to start at 0. Okay, so if I think of the x component, where is the x component going to be 0? It's going to be 0 here and here. Okay, but remember a sine function goes up first and then back down. Okay, see if we can avoid needing a reflection. So if I start at this point and go counterclockwise, I see that my x component is going to start at 0 and go towards its minimum. So that's not quite what we want. Whereas if we start at this point and move in a clockwise direction, we see that the x component starts at its middle value and moves towards the maximum. Okay. Now let's see if this same starting point will also work for part B, which asks us to model the y component by a cosine function. Well, at this point here, the y value is at its maximum, and as I move clockwise, I see that the y component is going to move towards the middle value and then eventually towards the minimum. So using this direction and this starting point, okay, will work well to solve both A and B. Okay, so let's set up our function. So for part A, where we're looking to model the x component, and again, we're doing it with respect to time. So my output value is going to be an x component, and then my input value is going to be a time value. Okay, so here we're going to be using sine function. We need an amplitude of 4, okay, and we need a k value of pi. Okay, we don't need a phase shift, so it'll just be pi t. Okay, and then the c value is just equal to 0. So this expression here, this equation here, represents the motion of the x component. If I start at this point, so starts at 0, and then it's going to move towards the maximum, back to the middle, to the minimum, back to the middle, and so on and so forth. Okay, so here x represents the x component of the position. Okay, and t represents time in seconds. Okay, now similarly for the y component, okay, so remember we're starting at this point here, which means we're starting at the maximum, okay, and then we're moving towards the minimum value, first the middle and then the minimum. So again, we don't need a phase shift. So again, our amplitude is 4, cosine, same period, so the k value still remains pi times t. Okay, and there we have it, our two equations. Now they ask us to graph that. I can, I'll leave that for you to do that. So we'll move on to part D, which asks us to show that x squared plus y squared is going to be equal to 16. Now, if you think of the way we've set up our model for the ride, well, wait a minute, it was just a circle of radius 4 centered at 0, 0. So we already know that the equation of this circle, okay, if I'm trying to describe an x value and a y value, okay, should be given by x squared plus y squared equals the radius squared, which is 4 squared, 16. Okay, so we know that that should already be the case, but let's see if that also works with the equations we have that define the components at each time value. Okay, so we'll take x squared plus y squared, which is equal to 4 sine pi t squared plus our y value for cos pi t squared. Okay, do a little algebra here. So here we have 16 sine squared pi t plus 16 cos squared pi t. Factor out the 16, and what are we left with in the bracket? Sine squared of pi t plus cos squared of pi t, which of course by our Pythagorean identity, this part here is just equal to 1. So I'm just left with 16. Okay. So in part E, we'll just do that orally here. It says explain why this relation is always true. Okay. So first of all, we have our sort of our geometric argument here that this is just the equation of a circle. So that's the equation that defines a circle. Okay, if we want to use a more algebraic argument, we can say that this identity, sine squared of an input plus cos squared of that same input, is always equal to 1. It's an identity that we've proven. Okay, so here we can say by the Pythagorean identity, okay, sine squared of any input, in this case here, our input is pi t, plus cos squared of that same input is always equal to 1. Okay, so for all theta in R. Okay, and that's it. That's essentially the problem here. So one thing to keep in mind, okay, if you move on to another calculus course, you're going to see that this is going to be another way in which we define a relation like a circle. Okay, is we think of finding an equation to represent the x component and the y component. So most of you will see something like this.